Hi, Cyprien here, and in this next video, let's talk about drive functions in OnScale. So I'll show you what is a drive function, how to create one, and how to assign one in OnScale. And we'll have a look at the kind of parameters you need to define a drive function, both in Designer and in Analyst. I'll show you also a few examples of different kinds of drive functions. And finally, I'll show you how to add a custom forcing or drive function. So let's start. So in OnScale, you have the drive function input tool, which will basically graphically show you what the drive function looks like. So you can directly select the type of drive function you want, the frequency of this drive function, and you'll get the code which is needed that you can paste into your analyst script. So the only thing which is a bit confusing is that you have a frequency shown in the drive frequency, but what you see, the graph you see, the plot you see here is actually a time curve. So you don't see directly the frequency. You could, and I'll show you afterwards how it looks like, but you'll have to do a fast Fourier transformation on the signal to actually see the frequency distribution, because OnScale is a time domain code. And before I start and actually show you how the code looks like and the different kind of drive functions we provide, let's come back to something very simple, and basically what is a forcing function and why it is actually required. Well, as I told you, OnScale is a time domain code, and this means that basically when you look at, let's say, a structural acoustic problem like a steel plate in which you want to see the propagation of the acoustic pressure. So you put a pressure on one side and you basically make this pressure, you give an impulse of pressure to one side of your plate. You are basically giving it a drive function because your pressure has to have this pulse in time domain, right? And this, the way the pulse itself is defined is by giving it a time distribution, which is called a drive or a forcing function. So it's the same thing. And what we look at is, okay, I send this pulse into the still plate. So I'm looking at several areas of my plate. What is the actual time domain response from the plate, from the acoustic pressure inside the plate? And from that, you can deduce a lot of characteristics about your system by looking at the output, knowing the input. Okay, so let's have a look at, now that we understand how it works, let's have a look at how to actually input that. So this is the toolbox. So it's very simple. You just select the type of function you want, the drive frequency. So and then you get the curve that you can insert. So in designer mode, you just click on insert, and in analyst mode, you'll have to insert the code of that, which will be generated using the preview syntax. And now in analyst code, this actually will look like this. So you'll have a func command, which represents this drive function, and it has certain number of parameters. So some of those you see here are the frequency, the amplitude, the phase shift, the number of period circles. So those parameters, I think, are pretty obvious what they do. And those value add and ramp cycle and T delay, they are a bit more difficult to grasp. So here I have a description of what they do. So the value add can be used to offset the function on the amplitude axis. The ramp cycle allows the user to specify how many cycles it takes to reach the maximal amplitude. And the T delay is simply a time delay applied to the function. So I'll show you some example of that right after. Before that, just let's switch quickly to OnScale Analyst. And now I'm reopening one of the models that I used in the previous video, which is a 3D transducer. And I'm looking at the analyst code here. So let's go and look where this func command is actually located. Okay, it's here. So you see here, so this comment here, and basically it's written here, driving condition. So this is it. This is the drive function. So it's defined like that. Func. This is the name of this. So it's called time func underscore one. This is the type of function it represents. So here, this means wavelet. So if you want to be sure what this means, you can right click and go in the doc, and you'll basically get all of those parameters. So you see the one here is the frequency, the 4 is the amplitude, the peak amplitude of the wavelet, and then you have several parameters which here are 0, and those are gamma, nu, and t delay, which are set to 0 by default. By the way, you have all the types of functions in the doc also here. So if you want to have a look at all of those, you can also have a look at the doc and read this. Now, what is interesting to have a look is where this function is actually defined. So how do I know that? Well, I can take the name of this. Let's copy that, and let's do a Control F and find where this is actually used in the code. Okay, and we see that, so we have one instance of that in the pout command. So which means that this will be what will be outputted out of this. And we have one here in the PS command. So, and this is where it's actually important here, because this time function represents the time amplitude which is used to define my voltage of my electrode. So this is my electrode definition, load 1, and this is the amplitude which is applied. And you see that the way basically to define this function is to use the keyword func and to append the name of the function to it. So you're getting func time func1, and this is what you'll get. Now, okay, so now probably what you're going to think is, okay, now I know that the code is written like this, but in Analyst, how do I actually know how to write this? Well, the time function tool that I was showing you before is also available in Analyst. So you can click here, open that, and you have to activate the preview syntax here. And you choose, for example, well, let's choose the same, the Rico wavelet with this amplitude here. Or we can change, we can use a Blackman Aris wavelet. So you see that it's slightly different. Well, not slightly, it's actually different, right? And this is the kind of code that we want. So I can click in here, copy and close, and then I just have to do a Control V to paste this here. And I can comment this, but I need to be careful because the name of this function is not the same. So if I wanted to actually use this one, so it's called tfunc, right? So I'll have to find where this one was defined. So that's the position I was showing you before, which is here. And I need to replace this by tfunc. Okay, and if I do that, so it's actually func tfunc, so that should be okay. I run the analysis, it will now use the new drive function that I defined. So that's how you basically define a drive function analyst. So you can use this tool to basically define the number of cycles, the amplitude, and the phase shift. So it's pretty straightforward to define a time function. Let me walk you through a few examples of those drive functions that you can define and the corresponding parameters. Let's look first at the sine impulse. So the sine impulse is defined using the func sine command. The first parameter is the frequency, and then one basically is for the amplitude, and then the one here in third position is for the number of cycles. So you see that there's only one cycle because this is an impulse. So we only send one cycle. And what we get here is the FFT of this one cycle. So how do you actually obtain this FFT? Well, let's have a look. Let's go briefly in OnScale post-process, and let's have a look how to obtain the FFT of my time function. So here's the post-process mode. I have already opened the result of a previous OnScale simulation, and this is the forcing function that I have been using, the sine impulse. So you can see here, this is only one sine cycle as an impulse. So the shape of the curve depends on the discretization of your mesh. So if your mesh is too coarse, this sine curve might look slightly less sine than it should, basically. So now how do I get the FFT of that? Well, it's pretty simple. You click one time here, and then the button here, FFT record, will be activated. You click on that just once, and here in the work tree, you'll see this FFT appear. Now, if I double click on that, I'll get both on the same graph, and I don't see anything. So the way to do it is to create a second viewport like that, and now I'm able to view the time curve and the frequency curve at the same time. So we see that the sine impulse has several harmonics. So sometimes this is a problem, and that's why generally wavelet type of functions like the Rico wavelet are much more used because they have no higher harmonics like that. Okay, so now let's come back to the PowerPoint and let's continue. Give me a few examples of other types of forcing functions. The continuous sine wave, for example, is basically the same than the previous, but the only difference is that the number of cycles here, I'm just setting that to 0. And if I set that to 0, the number of cycles will be infinite. So this is why it's called a continuous sine wave. And we see that in this case, the frequency obtained at the end is tending towards the perfect 1 megahertz frequency, right? Because the perfect infinite sine wave should have a frequency of 1 megahertz. So in practice, we see that because the signal is not really infinite, in practice, there is some small vibrations here, which are due to the fact that there is a certain windowing effect in the fast Fourier transform. Now let's look at another example, a 3-cycle burst with phase inversion. So in this case, the phase inversion is here. So I'm basically putting an angle of 180, and the phase here have all been inversed. So this is a phase shift. And I want 3 cycles, a 3-cycle burst. So I'm putting this number of cycles to 3. And this is what I'm getting. And if I look at the frequency response, I'm getting something like that. Now, let's look at the ramp-up 3-cycle burst with time delay. Now let's look at the ramp-up with 3-cycle burst with time delay. This kind of function is also a sine curve, but I am using the 2 other parameters that I haven't used up to now to show you what it gives you. So those parameters are the ramp cycle and the t delay. So the t delay is pretty obvious. I have added 3 microsecond time delay, and we see that in this function, basically there is a 3 microsecond delay. So it only starts after that. Now, the second parameter, which is set up to 3, called ramp cycle, what this does is that it ramps up the signal, and basically the maximum amplitude peak will be reached in the 3rd cycle. So that's why you see there is 3 cycles here, 1, 2, 3, and the amplitude is going up until it reaches the maximum here in the 3rd cycle. So that's the ramp up with 3-cycle burst with time delay. Now we have also the Blackman-Harris type of wave. So this one uses a different keyword. So if you see Funk Black, this is Blackman Harris, and it has only three parameters: the center frequency, the amplitude, and the time delay. And basically, what it does is that it's a window function applied to a sinusoid. So the window governs the amplitude of the signal and is used to reduce the spectral leakage. So you get something like that, a signal which is pretty broadband. So this is pretty useful when you want to analyze the response to a broadband type of excitation. Then you have the Rico wavelet, which is used very frequently in on-scale examples because this is one of the most versatile type of input. So it resembles a lot the Blackman-Harris. So sometimes more or less equivalent actually to use one or the other. The advantage is that this is a wavelet, and if you know about signal processing, the wavelets are very useful type of functions because they can be convolved with unknown signals and allow you to extract a lot of useful information from the output. So you can basically define one like this very simply: funk wave with 4 characters WVLT. This is the main frequency and 1, which is the amplitude here. So if you get a wavelet like that, which has the FFT will show you the center frequency here chosen was 1 megahertz. Now let's talk about the chirp. The chirp signal is a waveform which changes frequency linearly as time progresses. So it's used in sonar and kind of system like that because it's basically compressing the time signals a lot, and it allows you to basically to generate a wideband response to many frequencies into one signal only. As you can see, the frequency at the beginning is longer, and the frequency decreases when the time goes along. So this is what's called chirp, and you have the FFT on that as well. Now let's talk briefly about user-defined functions. Because of course you may have your own type of input function and you'd like to input this one into the software, so it's totally possible, and basically it's almost equivalent as giving it an Excel file and basically defining the function from this. So I'll talk briefly about how to do it, but before there's an important note. It's not always necessary to replicate the drive function exactly, because what some people do is that they see, okay, in my system, I must have this exact time input function, which is very weird shape and all that. So they want to input this into the software to look at the response, which is, it's doable, and they can do that actually. But if you think in a more effective way and also more computationally efficient way to analyze this kind of system, because it's a linear system basically, so it's much more useful to analyze the response to an impulse and then to basically use convolution method to simulate the output from any input signal. So basically what this means is that you send a Rico wavelet, for example, you look at the output, and from those two signals, you're able to compute the transfer function of the system, and you can obtain the response to any type of function. So of course, you'll have to be able to do a few simple math to do this. But if you're interested, you can send a message in the forum or to support, as we have a bit more documentation of that we can send you in case you are interested by this. Now, how do you add actually a custom function if you still want to do that? So the way I do it generally is like that. You start from the Excel file and you save it into formatted text space delimited type of format, so it's called PRN in Excel, and then you change the extension of the file to .dat, so you're able to import it in the designer mode. And if you do that, you'll get your second also, which is pretty fine. And actually, the way this should be into the text file is simply two columns with a space in between. So if you have a text file with two columns and space in between with those numbers into it, that will work as well. You just have to change the extension and you can import it in the designer mode. Now, how to import that in the analyst mode? So analyst mode, basically, there are two ways. So the first way is to define those values directly into your flex input file using the data command. So you do data hist drive one, which is the name of the history here, and 100, the number is the number of data. So if you have 100 data, you put 100. If you have 1,000 data, you put 1,000. You basically list your data like that in two columns below this, and when you do that afterwards, you just call this data when you define the function hist drive, and you can scale the data by a certain value as well. Now, a much more clever way to do that would be just to put that in a text file and to import it using this syntax here. Okay, and that's it for this lesson about drive functions. So I hope it was useful, and in the next lesson we'll talk about boundary conditions. So see you in the next video.